As a global maritime hub, Singapore continues to leverage on technologies to make our ports safer, greener, and more efficient. To achieve that, R&D serves as a catalyst for achieving MPA's goal in digitalization, decarbonization, and talent development. And we do it through research initiatives and programs strategized in collaboration with the Singapore Maritime Institute, bringing industry, regulator, and researchers together to work on various areas.
Singapore announced its national climate target to achieve net zero emissions by 2050 as part of the Long-Term Low Emissions Development Strategy (LEDS). Every sector, including the hovercraft sector, will need to meet this net zero target. From 2030, we plan for all new hovercraft operating in our port waters to be either fully electric or be capable of using B100 biofuels or net zero fuels such as hydrogen. Electrification is identified as one of the more feasible decarbonization pathways for our hovercraft sector to reduce greenhouse gas emissions. MPA plans to establish the charging infrastructure to support electric hovercraft operations in Singapore from 2025, and these 3 research projects will help make it a reality.
Our project seeks to develop an advanced data-driven simulation model to perform impact analysis and examine planning scenarios of large-scale hovercraft electrification for agencies' policy and planning consideration. Through our research, we extracted the operational schedules and patterns of our hovercraft and worked together with MPA and SMI on various electrification pathways to identify optimal charging infrastructure configurations. The AIS data tells us when the hovercraft is in a stay event or a trip event to determine energy consumption patterns, enabling us to identify where they may need charges and plan for different charging needs. With the hovercraft AIS data, we created a heat map to visualize stay events across the island. However, AIS data alone does not account for energy usage. We created algorithms to simulate accurate energy usage across different hovercraft classifications and activities. These insights gave a working model to study different charging behaviors and help stakeholders analyze what-if scenarios on hovercraft operator conservativeness to serve as a baseline for future hovercraft guidelines. This culminates in simulations that supplement our stay event heat map to give us a complete picture and foresight that matches our grid supply with charging requirements and locations, as well as timelines for infrastructure upgrades as we shape the future landscape of hovercraft electrification.
Transitioning to wireless charging is a key component for the hovercraft charging master plan, and there are huge benefits for the maritime industry to do so. Firstly, wireless charging equipment is fully contained and insulated, making it safe to operate in all conditions. Secondly, wireless charging equipment requires external supporting physical infrastructure, such as cranes and trained personnel to operate as part of the connection process. While wireless charging equipment is labor-free and adaptive to the hovercraft they service. Once the ship is docked, it automatically charges, saving time and manpower. However, implementing wireless charging isn't as simple. The onshore charging infrastructure has to be converted to wireless, and the increased onboard weight affects performance, especially for lighter vessels.
Our project works on minimizing the onboard weight, and we do so by redesigning existing hardware from the ground up. We studied the geometric shape of various coil designs and improved upon it to use less material while getting better energy output.
Industry standard equipment uses ferrite material for their magnetic coil designs. To reduce the weight, our proposal uses hybrid components, including nanocrystalline materials with high saturation flux density.
We have implemented power density modulation that allows us to control the voltage by skipping pulses. This innovation eliminates the need for DC to DC converter in both the onshore and onboard wireless charging equipment, significantly reducing the weight for both onshore and onboard equipment.
The final result of our prototype for onboard wireless charging equipment can generate twice the power output and thus double the charging speed, making electrification for hovercraft an exciting development.
As home to one of the greatest ports in maritime trade, Singapore will need to strategically migrate to more energy efficient and environmentally friendly operations through the electrification of hovercraft. Our project focuses on 4 work packages to make that possible. We start by developing the floating charger infrastructure. Solid-state transformers, SSTs, can be directly connected to our grid without disruptions. With the standardized requirements for an electric vessel fleet, we can scale it up safely in the marine environment. The advanced shore power charger provides electrical power to docked ships instead of diesel. This reduces air emissions and is cost-effective, providing more than 97% efficiency. To support the charging infrastructure, we have developed a Marine Energy Management System, MEMS, as an advisory system that plans and manages the optimal energy use in marine vessels. The MEMS comprises of 2 dashboards. For the vessel, the software provides intelligence from travel routes to weather conditions, enabling the captain to make informed decisions. For the port, personnel can manage timings to coordinate multiple vessels to optimize charging schedules to reduce the downtime.
To ensure that theory and practicality work hand in hand, we designed the Electric Craft Shipboard Kit to create digital models of the hovercraft in our waters to verify our electrification plan through simulation. This stress tests many interconnected variables relating to the maritime environment, the performance of the vessel, and its onboard energy systems. The insights and results we gain from simulating Singapore's maritime conditions have given us the confidence to replicate it across different physical conditions and vessels in other parts of the world.
Our first 3 work packages open up the possibility for us to scale up the end-to-end EV value chain and create the foundation of an energy-as-a-service model in the future.